Picture this. You're sitting there, maybe on your couch, and you're completely motionless.
Okay.
Your hands are in your lap. No controller, no mouse. You're not wearing some, clunky VR headset.
Right.
But on the screen in front of you, you are commanding an entire army in a game like Civilization VI. You're navigating these complex menus, you're directing units, all of it.
Yeah.
And you're doing it just by thinking about it.
It sounds like magic. Or at least like the opening scene of a good cyberpunk novel.
It really does. But then let's add another layer. Say your character in the game reaches out and touches some, a crumbling stone wall. Suddenly, you, sitting right there on your couch, you feel that grit. You feel the texture of the stone on your own skin.
That is the holy grail. That's the closed loop.
And that is exactly what we are unpacking today. We're not talking about sci-fi scripts. We are talking about the read and the write of the human nervous system. We've got a stack of sources here covering Neuralink's latest clinical trials, so getting data out of the brain.
And then the other side of it, this fascinating research on skin-integrated haptics, which is all about putting data back in.
It's the convergence of those two things that makes this moment right now so wild. I mean, we're in this 2025, 2026 window where this is all moving from just, lab experiments into something real.
It really is.
So the mission for this deep dive is, it's pretty simple. We want to figure out how we got here. We'll look at the engineering that lets a robot literally sew threads into a brain, the human stories like Nolan Arbaugh's that prove it works.
And then how we trick our own skin into feeling things that aren't actually there.
And honestly, the best place to start is with the read, the input. We have to talk about Neuralink because for decades, brain-computer interfaces, BCIs, they were kind of a nightmare.
Oh, they were horror movie props. I remember seeing these photos of early BCI patients, and they'd had these massive plugs just screwed into their skulls.
Yeah.
Wires everywhere.
Literally tethered to a server rack in a lab. You couldn't exactly go grab a coffee with that setup.
No, not at all. It was strictly clinical. And Neuralink's entire pitch was to change that form factor. They wanted to turn that whole server rack into something the size of a coin that just sits flush with your skull.
The Fitbit for your brain.
That's the line, yeah.
Yeah.
Essentially.
Yeah.
Wireless, inductive charging, fully implantable. But the hardware, it means nothing without a user. And that's why I was so gripped by the case study of Nolan Arbaugh.
Nolan's story is really the emotional anchor here, isn't it? He was the very first participant in the PRIME study back in January 2024.
Right. And for context, for everyone listening, Nolan is a quadriplegic. He had a swimming accident, paralyzed from the shoulders down.
And think about what his digital life was like before this. If he wanted to use, say, an iPad, he had to use a mouth stick.
A mouth stick. He's physically gripping a stylus with his teeth, using his neck muscles to just peck at the screen, one tap at a time.
My neck hurts just thinking about that.
It's exhausting, and it requires a caregiver to be there to set up the tablet, position the stick. He had basically zero digital independence.
Then he gets the implant. And reading the report on his progress, it's just baffling. He went from pecking at a screen to playing Mario Kart.
And winning.
And winning. But the one that really blew my mind was Civilization VI. I play that game. It is not a simple point and shoot.
Not at all.
It's menus inside of menus, complex strategy, map scrolling. Nolan was playing that for hours.
That's the key metric right there, the duration. Because the device is wireless and physically invisible to him, he was using it for these 12-hour sessions. He'd pull like an 8-hour workday practicing with the researchers.
And then what, just game for 4 hours?
And then spend 4 hours gaming or learning languages.
Yeah. The engineers, they measure this in bits per second, right? It's like an internet connection for your thoughts.
They do. It's the standard for BCI speed. Before Nolan, the world record for a human BCI was decent, but Nolan, he just smashed it. He hit roughly 9 bits per second.
That's like double the previous record.
Almost double. And you have to keep in mind, this is just of him thinking about moving a cursor.
So let's pause and actually look at how that works, because I think a lot of people have this idea that the chip is, reading your mind, like it knows your secrets.
Right.
But it's not reading thoughts, is it? It's reading the mechanics of thought.
That is a crucial distinction. The device is implanted in the motor cortex. So this is the part of your brain that plans and executes movement. When you want to move your hand to the right, that part of your brain fires off a very specific electrical pattern.
Even if your hand doesn't actually move.
Exactly. The brain doesn't care that the spinal cord is broken. It still shouts the order. The Neuralink telepathy app is basically just listening for that shout, decoding the pattern and then translating it into a Bluetooth command for the cursor.
But sticking a microphone into the brain to hear that shout, I mean, that's the scary part. The brain is so soft. It's like tofu consistency. You can't just shove a bunch of metal wires into it.
And this is where the engineering gets really clever. Old BCIs used rigid spikes, kind of like a tiny bed of nails. Yeah. But your brain pulses. It moves when you breathe, when your heart beats. And if you have these rigid spikes in moving tofu, you get scar tissue. And that scar tissue blocks the electrical signal.
So Neuralink went with these threads.
Flexible polymer threads, they're about 4 to 6 microns thick.
I tried to look up a comparison for that. A single red blood cell is like 7 microns.
Huh.
We were talking about wires thinner than a blood cell.
Thinner than a strand of spider silk. They're so light, they just float with the brain tissue. They don't tear it.
Okay, but here's the logistical nightmare. If I hand you a piece of thread that's thinner than a blood cell and has the structural integrity of, like, a wet noodle, how on earth do you push it into the brain? You can't.
A human surgeon definitely can't. Your hands would be too shaky. You couldn't see what you were doing. That's why they had to build the robot, the R1.
A sewing machine.
It really is a sewing machine. It has cameras that map the surface of the brain, and it automatically identifies all the blood vessels. Then it inserts the needle into these tiny, tiny safe zones between the capillaries to avoid any bleeding.
So it's like a sniper for neurons.
A very helpful sniper, yes.
But it wasn't a perfect launch. We have to talk about the retraction issue, because for a minute there, it really looked like the whole experiment might fail. A few weeks after Nolan's surgery, he started losing control. The cursor got laggy.
Yeah, the data rate just plummeted. And it turned out that because the threads are so flexible, and maybe because of some air trapped in the skull after the surgery, a bunch of the threads had actually pulled back. They slipped out of the brain tissue.
So the microphones were moving away from the speakers.
Exactly. The volume dropped. The signal was just noise.
And the obvious fix would be, okay, let's go back in and shove them back down, right? Another brain surgery.
Which is incredibly high risk. You do not want to open the skull twice if you can avoid it. So the engineers, they tried a Hail Mary. They just tweaked the algorithm.
A software update.
A software update.
Right.
To make it much more sensitive to the few threads that were still connected.
They just turned up the gain.
And it worked. Not only did he get full control back, but he actually beat his previous records after the fix with fewer working threads, which is huge.
Wow.
Because it proves the system is upgradable over the air. You can literally patch a human brain interface.
That is wild. And they've kept going. I was reading about the second participant, a guy named Alex. He's using it for CAD design.
Yeah, 3D modeling.
Yeah.
And he plays Counter-Strike.
Which is a first-person shooter. That requires twitch reflexes.
It does. And then there's Brad, the third participant. His use case is really poignant. He has ALS. Before this, he was using an eye tracker to communicate.
Okay.
But the problem with eye trackers is light. If he went outside in the sun, the sensors would just get blinded, and he couldn't talk.
That's such a specific, devastating problem. You go out to a park with your family and you lose your voice.
Right. Brad used the Neuralink to control text-to-speech software. Doesn't rely on light. It works in the dark. It works in the sun. It gave him back his ability to communicate in the real world.
So we have the telepathy app. That's the output, controlling cursors. But the FDA has also given breakthrough status to something called blind sight.
This is the flip side of the coin. If telepathy is the brain shouting out, blind sight is the world whispering back in. The idea is to bypass the eyes entirely and stimulate the visual cortex directly.
It's like plugging a camera directly into your brain's HDMI port.
Roughly, yeah. At first, it would probably look very low-res, like an old Atari game, just flashing points of light, called phosphenes. But for someone with zero vision, that's navigation. That's independence.
Which brings us perfectly to the bridge, the convoy study. They want to use the link to control a robotic arm.
Right. So imagine a future where Nolan isn't just moving a cursor around a screen. He's controlling a robotic prosthetic to pick up a glass of water.
But here is the problem, and this is where our sources on the other side of things get really interesting. If I numb your hand with Novocaine and I tell you to pick up an egg, what happens?
You're going to crush the egg, or you drop it.
Exactly, because you can't feel the grip force. You have no feedback loop.
You're flying blind, effectively. Visual feedback is not enough for dexterity. You need touch.
And that segues perfectly into the second half of our deep dive, the right, haptics. Because right now, haptics usually just means my phone vibrating when I get a text.
Or your Xbox controller shaking when you shoot a gun. It's primitive. It's a blunt instrument. We call it the buzzer problem.
The buzzer problem.
Yeah, think about VR today. You put on the headset, the visuals are incredible, 4K, realistic lighting. And then you reach out to touch a velvet curtain in the game, and your plastic controller just buzzes.
Like a pager from 1998.
It shatters the immersion instantly. Your brain just goes, nope, fake. This is fake.
So the source material on this skin-integrated tech is fascinating because they basically had to reverse engineer human skin to fix this. They had to figure out what touch actually is on a biological level.
And touch isn't just one thing. It's a symphony. Your skin is packed with these little sensors called mechanoreceptors. You have Merkle discs and Ruffini endings that handle pressure and stretch.
So that's how you know you're holding a heavy rock versus like a styrofoam cup.
Precisely. And then you have the vibration sensors.
The Meissner and Pacinian corpuscles.
And this is where the engineering gets super specific. The big critique of current tech is all about frequency. Think of your skin like a radio tuner.
Okay, I'm with you.
Most frequencies are just static. Your brain just tunes them out. But humans have this massive sensitivity spike right between 200 and 250 hertz.
That's the magic number.
That is the broadcast frequency for texture. If a device can vibrate at exactly that rate, your brain stops interpreting it as a generic buzz and starts interpreting it as, well, as something real, as friction, as grit.
So if my phone vibrates at, say, 100 hertz, it just feels like a phone. But if it could vibrate at 250 hertz, it might feel like I'm touching sandpaper.
That's the idea. But it's not just what vibrates, it's where. We have this sensory map in our brains, the homunculus. Our hands and lips are like high-definition 4K. Your back is standard def.
The two-point discrimination thing they mentioned in the study.
Exactly. If I poke your fingertip with two pins that are just 2 millimeters apart, you feel two distinct sharp points. If I do the same thing on your thigh, you only feel one poke.
Really?
Yeah, you need to separate them by like 40 millimeters, almost 2 inches, before your thigh realizes, oh, wait, there are two of them.
So if you're building some kind of haptic suit, you need thousands of tiny actuators in the gloves, but only a few big ones in the pants.
It's all about resource management. Yeah.
So let's talk about the hardware then, this electronic skin. The sources describe these as thin, sticker-like patches. What's actually inside them that's doing the shaking?
Well, we're moving away from the old school stuff, the ERM, the eccentric rotating mass. That's the little buzzer in your old phone. It's literally a tiny off-center weight spinning around.
I hate that thing. Sometimes I hear a phone buzzing on a table, and I swear I can feel it in my leg, even when my phone isn't in my pocket. Phantom vibration syndrome?
That's a real phenomenon. And mechanically, ERMs are just sloppy. They take a long time to spin up and slow down. We call it muddy haptics. It's like trying to tap out a Morse code message on a drum that's covered in blankets.
Okay, so what's the high-def version?
Well, you have LRAs, linear resonant actuators. That's a little magnet on a spring. It's much punchier. But the real cutting-edge stuff is in piezoelectrics.
Piezo sounds cool.
It's these materials that deform almost instantly when you apply electricity.
Yeah.
It's incredibly fast, and that allows for really crisp sensations. The click of a button, the snap of a twig underfoot.
There was one more method in the research that sounded a little terrifying. Electrotactile stimulation?
Yes. The zap.
That's literally shocking the nerves, isn't it?
It is. You skip all the moving parts, and you just send a tiny electrical current into the skin to fire the nerve directly. It's super efficient because the device can be paper thin, but there's a pain threshold. And the tricky part is that it changes based on how sweaty you are.
So if I'm playing a scary VR game and my palms start sweating, suddenly the gentle breeze on my skin feels like I'm being tasered.
That is the engineering challenge, yes. Calibrating for sweat.
But the biggest takeaway for me from the haptics report was this idea of spatiotemporal patterns. Because real touch isn't just one point vibrating.
No, not at all. Imagine someone poking you with a stick. That's a single point. Now imagine someone dragging a feather across your arm.
Okay.
That feather is triggering a whole wave of sensors. Sensor A fires, then B, then C in sequence. That sequence, that ripple across time and space, is what tells your brain motion. It tells you softness.
So these new skin patches, they use arrays of little actuators to play back that sequence. They can create a ripple across your skin that might simulate a spider crawling on you, or water running down your arm.
And when you combine that with that magic 250 hertz frequency, the brain just buys it. It accepts the illusion.
So let's bring it all back together. We started with Nolan playing Civ 6. We moved to electronic skin. Why do these two technologies need each other so badly?
Because of the robot arm, the convoy study. Just imagine Nolan in 5 years. He has the Neuralink. He thinks, grab the apple. The robot arm reaches out.
The read.
Right. But the robot arm has pressure sensors on his fingers. It touches the apple. It sends a wireless signal to a haptic patch on Nolan's shoulder, a part of his body where he still has feeling.
Right.
The patch plays a specific spatiotemporal ripple on his shoulder, so his brain feels the shoulder vibrate. But because he is watching his robot hand grab the apple, his brain merges the two events. He feels the apple in the robot hand.
That is the Luke Skywalker hand.
It's sensory substitution. The tool becomes part of your body.
It's incredible, but it also opens up some pretty heavy questions. I mean, we are really blurring the line here between biology and technology.
We are. And we have to talk about the data privacy aspect. Neuralink is reading intent. If I'm using the telepathy app to type an email, technically the system knows what I'm going to type before I even type it.
It knows the draft before you hit send.
Who owns that data? Is it protected like your medical records? Or is it just user data that gets sold for ads? Hey, we saw you thinking about pizza. Here's a Domino's coupon.
That is a deeply dystopian thought. And then there's the access issue. This requires a surgical robot, a team of neurosurgeons, custom hardware. This isn't going to be cheap.
Not for a very long time. We risk a serious class divide if this tech eventually moves from therapy, fixing paralysis, to enhancement, making you type faster or remember more. We could have a society of enhanced wealthy people and natural everyone else.
It's the classic sci-fi warning. But for now, for people like Nolan and Brad, it's not about enhancement at all. It's about getting their lives back.
And that's the grounding truth here. For them, the risk of brain surgery, and it is a big risk, infection, hemorrhage, all of it, is worth it for the chance to communicate, to interact with the world again.
It's a fascinating time to be watching this. We are literally seeing the interface disappear.
We're moving from using the computer to being the computer.
And on that note, I want to leave everyone with a final thought to chew on. We talked about reading intention and writing sensation. If we can perfectly read your desire to move your hand, and we can perfectly simulate the feeling of that hand moving and touching something, does it actually matter if the hand is made of flesh and bone or carbon fiber and silicon?
If the experience is identical, maybe not.
At what point does the machine stop being a tool you're using and just become you? Thanks for diving deep with us.
See you next time.